Well, good morning, dear, and welcome back. So, in this lecture, we'll try to recapitulate the concept which I described in my earlier lecture about regularization, and we'll focus more on the algorithmic part of regularization, which actually automate how many parameters should be there, giving a sample for designing a, say, for example, machine learning model like linear regression model. So just the concept, if you recapitulate, so this is my predictor, and in a democratic way, I have selected so many parameters, whichever I want. Okay, and then I am using regularizer term, okay, to show that the necessary parameters will remain and unnecessary parameter will vanish. How the things will happen, to some extent, of course, how the things will happen, that we are going to understand with the example of a L2 regularizer or so-called reach regularizer. So pay your attention here. So this is my cost function, okay, and this is the loss function, that is ground truth minus the difference between ground truth and the actual value. So this is loss, plus we have a regularizer here, lambda j times summation of j equals to 1 to n wj square, and j is the feature, okay, number of features. The wj is the jth feature, and we are assuming that there are n number of features. Now, normally, instead of attaching and lambda is a hyperparameter, as I have told you earlier. So normally we keep wj fixed, otherwise it will be too complicated. For every parameter, you will have to define a or assume a different lambda. Instead, we just make lambda j equals to lambda. And then if you differentiate this function with respect to, so this is, we'll have to do, right? This is my gradient descent algorithm. Wj assign equals to wj minus alpha, derivative of the cost function, and alpha is known as step length of the iteration, or it has a fancy name called learning rate. Learning rate. Okay. So you see now when I am differentiating this 2m mathematical convenience, so after differentiation this 2 will come, so 1 by m, so this is the derivative, we have deduced it, plus this 2 is still coming, so lambda by m wj, okay, because we have differentiated with respect to wj. Now multiplying it with learning rate, we will be getting this expression. Very simple. So now let us see that how the gradient descent algorithm will look like with regularization. So this is wj assign equals to earlier wj minus alpha divided by m, summation of I equals to 1 to m, number of samples. This is predicted value minus actual value times x j. Okay, x is a feature. Okay. Minus alpha times lambda divided by m wj. Okay. So this, because of this minus and minus. Now look carefully. I can do a little math here, arithmetic here. Just wj and wj. I am just taking this part common. 1 minus alpha times lambda divided by m wj minus alpha by m, and this is the term. Okay. Now you see, very interesting observation you can make about the term, this one 1 minus alpha lambda divided by m, and let us call it beta. So normally what alpha is, learning rate, right? It is 0.1 or 0.01, normally small, okay, 0.001 depending on the type of the nature of the cost function. Okay. So you have determined the step lengths because you do not want to miss the optimum value. So lambda equals to say 1, 2, 3, it could be 100, it could be 10, 1000, like that. So it's another hyperparameter which is to be attached with the parameter. Okay, and m is the number of the samples. Now, if n is really, really large, say 50,000 million, okay, so this term, irrespective of whatever the value is this term is really very, very small. So what does it mean? Means you have now, I'm trying to just show you pictorially, okay. Okay, you have millions of samples, okay, and perhaps to capture, and if the samples are like that, it has hidden pattern which is not very straightforward, so definitely you will have to make a complicated predictor having a large number of parameter attached to the large number of features, right? So in that case, what is going to happen, you see, if n is large, so this is very insignificant. That means the parameter will be shrinked, right? There will be a shrinkage of the parameter by every step. But that shrinkage itself is very, very small. That means many Wj are going to stay there, and which is justified because M is quite large, and you require a number of parameters, more number of parameters to be attached with more number of features, okay, to capture completely the pattern here. On the other hand, if the M is small, okay, M is very, very small compared to N, so N should not be, you see, then what will happen? 1 minus something, like 1 minus something is quite appreciable now, okay, 0.5, 0.6, 0.7 will be the value of beta, maybe, okay. That, what does it mean? That means you, even if you are taken a large number of n, and you don't require, because you have simple model can fit over some of the few datas. In that case, then what is happening? The W will be vanishing quite, shrinking of the W will be quite fast. So automatically, based on, of course, I have told that number of samples, this is one side of the game, because same number of samples, so if the same number of samples are actually aligned like this, then of course n will be less, and that will be also taken care of by the by this regularized upgradation rule, because you are calculating the loss, right? So if I just try to give you an example, say a little bit oversimplified example I am giving, say this is, and this is W, okay, and you have you are running for a particular W1, say this is your nature of the cost function, and you want to reach over here. So whatever is the value, so that will be your, say this is W1 value, and attached with the parameter, with the feature x1, okay. So W1 you received like, got like this by running gradient descent algorithm. Now say another feature you have, and it's just like W2. So W2 also you will get by running gradient descent algorithm. So this is W2, which can be attached with another parameter x2. And in this way, if you are running each parameter, you need to upgrade, okay, in a loop, and it will so happen, if the sample are such, then you may end up in getting some W, which is this is 0, right? So it's near about 0, or you can have something like this, near about near about 0. So W0 will be 0 here, and it could be like this, okay. So near about 0 kind of thing will happen, and that will be determined by the regularizer, okay. So I believe that you have understood how regularizer is trying to automate to some extent based on the sample characteristic of the sample, okay, because all the since you have done the gradient descent algorithm in our earlier assignment by using only numpy, not with the function, so you know how parameter is being upgraded with the samples. So nature of the sample, the parameter will depend on the nature of the sample, how the samples are, okay, and how the samples are distributed actually, and accordingly the regularizer will try to fit the optimum model with the parameter. So this is what I was trying to convey, that regularizer has a great effect in automating the model design process. Okay. Now let us see how regularizer can also be used for linear regression model which is written in a matrix form, the normal form in a matrix way. Using matrix we have written this. Okay. So already we have reduced, this is the parameter W equals to x bar transpose times x bar, where x bar is a design matrix, and we have dimension of x bar transpose times x bar n plus 1 cross n plus 1. So inversion of that matrix times x bar transpose times y is the level. Okay. So the design matrix actually, design vector, this is the vector, x bar belongs to the range space m cross n plus 1, y equals to m cross 1. So these are the things which we have deduced in earlier in my lecture for how to derive the normal equation in a matrix form. Now we are adding a regularizer term, and you know what was the disadvantages there. Disadvantages was this, right? So if you have millions of data or several thousand data, and this matrix is really large. So there are so many rows and columns in this matrix, and who knows that one row or one column out of them may be redundant, and then the matrix will not be of full rank, meaning that determinant of the matrix will be 0, and then you will not be able to figure out the parameter value in those cases, right? Those cases can be easily avoided. Just you see, look here, just adding a regularizer term. So what we have done here, so this is m cross, this is n plus 1 cross n plus 1 matrix. We have added a regularizer alpha lambda, and say this is a matrix L. We have so we are multiplying it. So W equals to actually x transpose plus lambda times L. This will be inverted now, and then all other remains like this. So you see, L, nature of the L is actually for first row, because we do not want the first parameter W0 to be regularized. Reason I have already told. So this is 0, and then 0 1. So this is a unitary kind of matrix. 0 1 0 times this is a unitary matrix, but all are multiplied. 1 is multiplied by lambda, third position multiplied by lambda, like this. Okay, you have got the rhythm. And what you have done in doing this, you see, with this matrix, with this row, you are adding lambda term. And even if now the two row earlier were similar, by virtue of adding lambda at different places, right? So they will not be similar anymore, and you would end up in not getting the determinant of this matrix 0. So always the regularizer will ensure that always the inversion of such matrix exists. So you see, regularizer has a great effect, positive effect, even in matrix form of normal equation of linear regression model. Okay, so this lambda has to be greater than 0, any value, positive value. Okay. Now we are going to discuss very interesting thing, that how to create a regression model, linear regression model with regularization, starting from the data which you have been given. So you have, the moment you get the data, assuming that data is pre-processed, data engineer has given the data to you after pre-processing. And then you have got the data. Moment you got the data, you will just need to divide it into two parts. Okay, training data and test data. Normally, whatever data is given, some 80% are normally used for training purpose, 20% used for testing purpose, or you may 70% you may use for training purpose, 30% you may use for testing purpose. Okay, so so this if 70-30 will be more robust, of course, because if you test data is large, then you can validate with a large number of data. But it is your choice. Okay, normal 80-20 or 70-30 or sometimes 60-35, 65-35, whatever, right? So you divide. Suppose 10,000 data you have been given for housing price data in Canadian city means, or then you can easily do 80-20 means you can easily use 8,000 data for training purpose and 2,000 data for training purpose. Now, you see, we actually also need to keep validation set out of the training data. Why we need to do that, I will try to explain using this simple diagram. Say this is my original data set, and we have split it into two parts, and then we are trying to do what we are trying to do. Training set is again subdivided into two parts, training and validation set. That means out of 8,000, 2,000, out of 8,000 itself, say I have now 6,000 for actual training, where I will run the gradient algorithm and I will determine the parameters, and 2,000 I will use for validation. It's just like testing. Validate means I will have to validate whatever parameter I have got, how much percentage of error I am getting in this 2,000 validation set. So that's the job of validation set. Now, the 2,000 validation set which you have used earlier, in the second iteration, you can make this 2,000 validation set as a part of training set and take another 2,000 data which earlier was taking part in the training set as validation set. And in this way, you can continue the iteration. Okay, so this was the validation set. Now, this was the validation. So each time 2,000, 2,000, 2,000. Okay, so idea is clear, right? That validation set is not fixed. So sometimes they are also taking part in the training process. Sometimes they are taking part in the validation process. Okay, so this, in doing so, what we are achieving, actually this is incidentally technical term, this is known as k-fold cross validation. Now, using a validation set and designing the validation set in the process of parameter tuning in this way ensures that optimization of the parameter. How? You see, the training set is for tuning the parameter. Now you tune the parameter and you got with validation set some error. Okay, and you just keep these W parameters. Okay, W parameters together with the error for iteration 1. Okay, keep somewhere. Then you are using different validation set, and then again designing your parameter, running gradient algorithm. Okay, say this is your Wj, E error you are getting corresponding to your iteration 2, then Wj error you are getting iteration 3, Wj error you are getting iteration 4, like that. Okay, so this is actually k value will be 4 because you have decided that out of 8,000 data, I will use 6,000 for training and 2,000 for testing. If some of your friend can decide, no, out of 8,000 data, I will use 7,000 for training and 1,000 for validation, then can you tell me what will be the k value? Obviously, k value will be 8 because 8 times you will just slide this validation set and you will get 8 set of parameter with error, validation error. Okay. So this is now you have. Now you can optimize. You see, sometimes with some validation set you have got less error, some validation set you have got more error. So one thing you can do, very simple thing, that simply take the average of all these parameters. That is the optimization, right? Average of all these 4 times you have got parameter set and take an average value. Another thing what you can do, you have um, W attached with the validation error, and you try to see, okay, this is the minimum validation error. So I will give corresponding to minimum validation error, the set, the parameter maximum weightage. This is a design, okay, this is your choice, and you can do that. That maximum weightage should be given to this. No, I will not simply average them, but I will make a weighted average, and your design could be much better. And in that way, you fix now the parameters. And once it is um, fixed and satisfied by the designer, then the predictor is done. Predictor design is over, and then you produce the final model. And with that final model, you test. So what is the test error? If it pass the test, for example, you do not want more than 5% test error. So if you use more than 5%, then you will have to go back and then again start from here. So you will have to make validation set different, and then you will have to have more kind of iteration, and that's all you can do actually. And you will have to optimize the model parameter, and you will have to redesign your um, predictor, and in this way the design will continue till you are satisfied. So once you are satisfied, your design is over, and you can use it now for future prediction. Is it clear? So this is actually how the I have taken the example of linear regression model, but this is valid for any machine learning model. Similar kind of approach, similar kind of ideas are also there in designing any model in machine learning paradigm. Okay. Sometimes deep learning also. The validation set will be there, training set will be there, testing set will be there. So you clearly now understand the difference between validation set and test set. For different purpose they are used. Okay. So with this, I think stay safe, and if you have still some problem, come back to the discussion forum, and we have given several assignments, and I suggest that as far as possible, do not use any library at the very beginning of determining of coding the gradient descent algorithm. You can use NumPy and just do all these assignments religiously, and you will understand whatever we have discussed so far theoretically. You will also understand practically. Okay, stay safe and bye bye.